figure shows a segment OQ of a straight wire carrying some current. For convenience, we have chosen a Cartesian coordinate system in which the x-axis coincides with the length of the wire. The point P at which it is desired to obtain the magnetic field is taken to be in the xy plane. The position vector of the point P is vector r is equal to x, y, 0. Consider now an elemental section vector dl of the wire at the origin of length dx. Then vector dl is equal to dx 0, 0. The coordinates of point Q are x, 0, 0. To use the equation, vector B is equal to mu 0 I upon 4 pi into integral of vector dl cross vector r upon r cube. Vector dl cross vector r should be obtained. Vector dl cross to vector r is equal to dx 0, 0 cross x, y, 0. That is equal to dx cross to cat vector I cross x into cat vector I plus y into cat vector j. Vector dl cross to vector r is equal to y into dx into cat vector k. Equation shows that vector dB is directed along the z-axis. Now, modulus of vector r is equal to x square plus y square raised to half. Therefore, r cube is equal to x square plus y square raised to 3 upon 2. Using equations and equation in equation, we get vector B is equal to mu 0 into I upon 4 pi into integral of y dx upon x square plus y square raised to 3 upon 2 into cat vector k. In this equation, I is the current through the conductor and the integral is to be taken over the entire length of the wire. When the wire is very long, ideally that of an infinite length, the integral can be considered to extend over limits minus infinity to plus infinity. In that case, equation will assume the following form. Vector B is equal to mu I upon 4 pi into integral minus infinity to plus infinity of y dx upon x square plus y square raised to 3 upon 2 into cat vector k. To evaluate this integral, we write x is equal to y tan theta, where theta is the angle QPO. Therefore, dx is equal to y sec square theta d theta. Taking theta as positive towards the direction plus x and negative towards the direction minus x, we get x is equal to minus infinity. Therefore, theta is equal to minus pi by 2, and x is equal to plus infinity. Therefore, theta is equal to plus pi by 2. Using these equations we get vector b is equal to mu 0 into I upon 4 pi into integral minus pi by 2 to plus pi by 2 y square sec square theta into d theta upon y cube sec cube theta into k cat vector. That is equal to mu 0 into I upon 4 pi y into integral minus pi by 2 to plus pi by 2 cos theta into d theta into k cat vector. This is equal to mu 0 into I upon 4 pi y sin theta minus pi by 2 to plus pi by 2 into cat vector k. This is equal to mu 0 into I upon 4 pi y into 1 plus 1 into cat vector k. Therefore, vector b is equal to mu 0 into I upon 2 pi y into cat vector k. Considering the symmetry of the problem, it is clear that the field will have the same magnitude for all the points located on a circle generated by rotation of the point P about the x-axis as shown in the figure, and at any point on this circle its direction will be along the tangent to this circle at that point. Thus we see that the magnetic field lines due to a current I flowing in a very long, ideally infinite wire are circular in shape as shown in figure, and the magnitude of the intensity is given by modulus vector b is equal to mu 0 into I upon 2 pi y at a point located at a perpendicular distance y from the wire. The direction of the field lines is such that if we hold the wire in our right hand with the thumb pointing along the direction of the current, then the fingertips point along the field direction as shown in figure